Well, thanks, Jeff, and thanks for inviting me to speak today. So I'm not going to talk about the PopART trial today. I'll be talking about that first thing tomorrow morning. So what I want to do today is to start really from the premise that we're a few years down the line and that we don't need to make the case for treatment as prevention. The case has been made. The efficacy demonstrated in 052 is stunning, and the mathematical modeling tells us that under certain assumptions, if we roll this out, we can get very high effectiveness. So the question is, so really we're in a situation of great optimism, but I think that the scientific process requires us to continuously trade off our inner optimist and our inner pessimist. So if you like, this talk is a kind of dialogue with myself, my inner optimist and my inner pessimist. And my inner pessimist has come up with 7 reasons why treatment as prevention might fail, and I'll finish on a cautiously optimistic perspective. I think the optimist won. So everybody has their list, and this is pretty much the list, I think, and how the list is organized. This is pretty much the list as it came out with all of the people who responded to the sort of call to arms of modeling the Granic et al. Paper in the Lancet. And a lot of people wrote in letters saying, what about this, what about that? And here is a list. All of these things could make treatment as prevention fail. Poor delivery, if we just can't get the testing and treatment out into the field. Poor uptake. So if it's in the field but people don't want it. Poor adherence or poor efficacy. So if the results of 052 are not generalizable because people in the field don't take their pills or engage more frequently in anal sex or other confounders, which mean that the efficacy in the field is lower. In the long-term, transmitted drug resistance, increased risk behavior, particularly in those who are untreated or undiagnosed. Number 6 is slightly more complicated. If there's a core group of people, so if most people go along with treatment as a prevention, but if there's a core group of people who are having more sex amongst themselves with other people and who at the same time don't take up treatment as prevention, that could be problematic. And the 7th one, which I'll speak in more detail, is acute infection drives the epidemic. So the perspective I'm going to give you, I mean, these are sort of points in the field, but the perspective I'll give you is a modeler's perspective. So I've been modeling in some shape or form treatment as prevention since about 2003, and developed sort of some perspective on some of these. And I'll go into different levels of detail. So the first ones are poor delivery, poor uptake, and poor adherence, poor efficacy. So the first thing I'd like to share with you is some results which I'll go into more detail tomorrow. This is a sensitivity analysis of a model. This is a model that we happen to use for the PopART intervention, for the cluster randomized trial, for the power calculations. And we did a multivariate sensitivity analysis on the different parameters. And the slope is how much they influence the outcome. So the different parameters influence the outcome a different amount. Now, it's a little bit tricky to interpret this as one factor is more important than the other because of the scale in which they're measured. But we found that by far the most important factor was the effectiveness. So for each point of percentage point change in effectiveness, there was a 0.93 percent point in the effectiveness of the intervention. Other parameters were the coverage of the annual test and treat campaign, so how many people got tested and started treatment, the behavior reduction, the treatment failure and dropout rate per year, and the take-up of male circumcision was much less important because of the lower efficacy and the dilution of the fact that it only applies to men and not to women. These are based on short-term predictions. These slopes might change in the longer term. So circumcision, for example, might be more important in the longer term. So that's a sort of one modeling perspective, and this could be done, this kind of sensitivity analysis could be done for different models and different settings over different time horizons. The second thing I want to report on is a discussion that we had at the WHO a couple of weeks ago about what metrics should be used in the field and at national level or subnational level for monitoring progress in treatment as prevention. There are different metrics proposed. One which has gained traction recently is community viral load. The annual infection risk, though the difficulty with that is that it depends on different individuals and different risk groups, not just on treatment status, and the proportion suppressed. So the community viral load has gained a lot of traction with a couple of articles. The TasP et al. Article cited over 100 times in less than a year since it was published in PLOS One. I think the community viral load, even though it reduces a complicated outcome to a single number, in actually reducing it to a single number, it ends up with something which is a little bit difficult to interpret because you're not entirely sure who you measured it in, and you're not entirely sure how the viral load itself translates to infectiousness. So changes in community viral load seem more complicated than they need to be. So the relationship, I mean, one way is to turn it into a transmission rate using these graphs here. I've illustrated one graph, but it could be used by changing it into a transmission rate or an annual risk of infection with these kind of graphs. But I wonder if the principal dichotomy isn't simply whether people have a suppressed viral load or not. So if you look, really the transmission rate is, we now know, pretty much very close to zero for people with very low viral loads, and you're either in that category or you're not, really. Subsequent changes between 10,000 and 50,000 seem a little bit less important. And this is sort of built into how we formulate the models, and it suggests that maybe we should focus just simply on what's referred to as a treatment cascade. And even though it's more numbers, it actually turns out to be, I think, simpler to interpret and also maybe easier in the field to make sure that is measured in representative populations. So just measuring the percentage infected, of which another percentage are diagnosed, of which another percent are treated, of which another percentage are suppressed. So if you know those four numbers, or even at a push just the top one and the bottom one, you have a pretty good idea of where you are in terms of progress towards treatment as prevention. So that kind of suggests that if you were designing a target product profile for a point-of-care viral load test, obviously you'd want it to work everywhere, be really cheap, be really robust, but maybe you only need it to produce a dichotomous outcome, positive or negative, maybe positive if your viral load is above 1,000 and negative below. Maybe that's sufficient. So the next issue I want to look at is transmitted drug resistance. I won't say a lot about that. The models differ amongst each other. Not everybody agrees whether drug resistance, transmitted drug resistance will become a big problem in the future. What all the models do agree on is that if resistance emerges, it will emerge slowly over years and decades, and that good adherence reduces not just the acquisition of resistance, but the spread of resistance. So once again, good adherence will be key. And also suggests that as long as we've got surveillance in place, we will have time to respond to emerging resistance, even if it does become a problem, and adjust the treatment as relevant. Numbers 5 and 6 are increased risk behavior, and this core group of high risk, low uptake. So the models are unambiguous about this. This really does matter. So these issues may be problematic. What we don't agree on is how much behavior change has occurred so far. So how much reversion to the norm is there? It's maybe a little bit hard to accept that there would be further increases compared to where we were in the pre-AIDS years, though frankly we don't know. And one of the things which will be incredibly useful will be the data collected from the population trials, which we heard about yesterday, PopART and the Iringa study and the NRS studies, the cluster randomized trials, which will include a lot of very important qualitative work. Who's testing, why are they testing, who's starting treatment, and correlating that with behavioral information on risk-taking. So the seventh point I want to go through is acute infection driving the epidemic. So clearly, if acute infection is driving the epidemic, then treatment as prevention will work in chronically infected people, but it won't stop the epidemic. So this is a long-standing, ongoing debate. I think the issues are clear. The data are much less clear. It turns out what I'm going to do is to try and summarize a lengthy discussion, debate, in between Brian Williams and colleagues on one hand, Mike Cohen, Kim Powers on another hand, and myself, that we had in a HIV modeling consortium meeting funded by the Gates Foundation a couple of months ago in South Africa, and which is shortly to be published in PLOS Medicine. So the first thing is that turns out we have very little data. The data we have are from Rakai, from the paper of Wauer et al., published in 2005, which directly assessed how much transmission occurred in couples in the first months of infection compared to later on when they become serodiscordant couples. A very influential study, and so influential that these data have now been interpreted and reinterpreted many times. So the first point that was made by Brian Williams, quite validly, is that though it is what we have, and it's not going to be replicated, try to think about replicating the study design. It can't be done, maybe retrospectively, but certainly not prospectively, because you couldn't leave the serodiscordant couples as a control. So this is all we have. But all we have is 23 couples in whom 13 transmissions took place in the first 5 months of infection, and the transmissions were not confirmed genetically. So we actually have very little data. So that's the first point. The second point I want to make is that even if we take the data at face value, there's a lot of flexibility for interpretation. So the first measure of how much transmission is due to acute infection was actually in the paper itself. The authors chose not to emphasize it because it was a biased observation. But if you actually look in the paper, of all of the transmission they observed in couples, 11% of them were due to this acute transmission. They emphasized instead the relative risk of transmission, not this number, which they felt was less biased. Fair enough. In a reanalysis, we use slightly more sophisticated statistical methods, but we also emphasize the role of the behavioral context and the partnership formation rates, and we provided a lower bound estimate based on the relative risk in Rakai, that if the partnerships was mostly of the form of serial monogamy, we would get 9% of transmissions during acute infection. At the other extreme, if we assumed random mixing between individuals, we got 32% random mixing. In a third analysis, Jeff Eaton, Tim Hallett and colleagues modeled this with an individual-based simulation with long-term concurrency, so somewhere between random mixing and serial monogamy, and depending on the level of concurrency, found between 16 and 27% of transmission due to acute infection. And in a final analysis, Kim Powers and Mike Cohen and Bill Miller and group, published in The Lancet last year, showed that if you had a core group of people, this core group was defined based on behavioral parameters in Malawi, but still the relative risk was based on the Rakai study, that if you had a core group of people who are high-risk individuals with concurrent partnerships, then the proportion of transmission due to acute infection could be as much as 38%. So just to emphasize, this debate about acute infection is often couched in biological terms, but the behavioral context actually has more influence on the overall outcome. Now, just to kind of finish, I want to explain an argument which is quite complicated, which was first made by Brian Williams in mathematical terms, and I want to show it to you in slightly different terms because I think it's an argument which is extremely important, is that in the end, though we have a lot of uncertainty, it may not matter that much to the predicted efficacy of treatment as prevention. So just to show you, sorry, if I use the pointer on this side, Okay, I'll use the pointer on this side. Sorry for the people on that side. So I constructed two versions of a conventional mathematical model. One where, for behavioral reasons, acute infection, shown in green, makes a small proportion. So this is sort of histograms over time. So it starts off in the early stage of the epidemic, about 25% of infection due to acute infection, and it settles down to about 10%. And I make a model where I allow for much more transmission during acute infection, starting out at 75% and settling down to about 30%. And the thing which I do, which changes everything, is I fit the model to the epidemic. So the model is shown fitted to the South African epidemic. The green is the prevalence, and you can see the two different models fit very similarly, and the red is the incidence curve. And on the right, I then introduce treatment as prevention from 2012 onwards. In the right, you can see for three different scenarios, an optimistic scenario, a pessimistic scenario, and a middle scenario. You can see the predictions of the two different models in terms of the cumulative reduction in incidence, I think measured over 2 years. It doesn't make much difference, the time horizon. And you can see the two models agree remarkably. So despite the fact that there's huge differences in acute infection, the outcome, the predicted reduction in incidence, is virtually the same. So how can that be? Well, it's because acute infections, if you change the amount of acute infections, it doesn't just change our prediction about what happens in the future, it changes our interpretation of what happened in the past. So let me just try and explain that briefly. So it's encoded in this equation here, which I won't go into. I'll give you a graphical explanation, just to say that this is what mathematicians call a beautiful equation when they talk about mathematical beauty, because it relates quite different concepts to each other. But basically, acute infections, we have to explain what happened in the past, and we have to explain the exponential growth of the epidemic. And we know the exponential growth in the South African epidemic. It was documented. It corresponds to a doubling time of the epidemic of about 1.22 years, or a growth rate of 0.56 per year. Now, if we're interpreting the past as driven by chronic infection, if chronic infection dominated this growth, then this is actually quite fast, because the average duration from one infection to the next should be about 5 years. If, on the other hand, this is predominantly driven by acute to acute chains of transmission, this is actually rather slow, because acute infection only lasts weeks to months, so a doubling time of 1.2 years is slow. And this epidemic, so if the epidemic was driven by acute infection, then actually the epidemic was very slow and it's on the verge of extinction. So one of these two statements needs to be true, and we don't need to know which one of the two statements it is. So I can illustrate this graphically. If you have a chain of infection, and in yellow you have these acute to acute transmissions, and in white you have transmissions during chronic infection, this epidemic here is got a low basic reproductive number. Each person only infects 2, and treatment as prevention, though it is compromised by the fact that there's a lot of acute infection, it doesn't need to do very much to put this epidemic into reverse. On the other hand, if the same pattern of growth was driven by lots of chronic infection, then that means that each person must have been infecting more people, the R0 needs to be higher, and treatment as prevention needs to do more. So treatment as prevention can do more in this setting, but it's got more to do. And it turns out those things trade off exactly in both simple models and complicated models. And in the end, the answer is that the role of acute infection doesn't matter so much. What we don't know, and this is sort of the next question, is we don't know when this argument, this strong argument, breaks down, and we don't, of course, know whether it happens in reality. Yep, my conclusions. So treatment is, so I've covered the 7 reasons why it could fail. I think mathematical modeling sheds some light and shows that though there are lots of hurdles and barriers, there are also many reasons to be optimistic, and treatment as prevention holds extraordinary promise. And in terms of facing all of these hurdles, I thought I would finish with a quote of the person who may well be the person who needs to make the decision to ramp up the expenditure over the next few years. And the quote is, "The real test is not whether you avoid failure, because you won't, is whether you let it harden or shame you into inaction, or whether you learn from it, whether you choose to persevere. Thank you.